There are a few properties of derivatives of vector functions that I'd like to make you aware of because they will show up from time to time. Most of these are simply retranslating properties of derivatives that we already know from Calc 1 into a multivariable calculus and derivative of vector function sense. So first thing is, if you're taking the derivative of a constant multiple times a vector function, you can ignore the constant multiple and simply differentiate the vector valued function. So this is your constant multiple rule as applied to vector functions. For the second, if you have a sum or difference of vector functions and you're differentiating that, then it will be a sum or difference of the derivatives of those vector functions. So that's the sum and difference rules. Again, this is basic, straightforward Calc 1 stuff, just applied to vector functions rather than traditional functions. For number 3, we have a form of the product rule, but this time we have a scalar function times a vector function. So it works the same way as the chain rule does, where you differentiate them one at a time. Sorry, I'm making that look too much like a dot product, but really it's just a product. So first times derivative of the second plus the second times the derivative of the first. The order in which you write those things doesn't particularly matter. But this is one form of the product rule. Same goes for number 4. If you're taking the derivative of a dot product of two vector functions, what you're allowed to do is differentiate one at a time and dot the results. Now, again, the order in which you write them doesn't particularly matter due to the fact that the dot product is a commutative operator. So this is another form of the product rule. Now, for number 5 here, the derivative of a cross product, the order in which you write these is really important because, as we know, the cross product does not commute. It is, in fact, anti-commutative. So, when you're differentiating them one at a time, be sure to write them in the appropriate order. If R is on the left and U is on the right, then it needs to stay R on the left and U on the right. Now, the order in which you write these two quantities doesn't particularly matter. You could reverse these, and that would be okay, but you cannot reverse the order of the actual cross product. If it's R cross U, it's got to be R cross U in both of your derivatives. That's the first 5 properties. This is another form of the product rule. We don't really talk about division of vectors, and that's a good thing, so you won't see the quotient rule in here. But this is a form of the chain rule. If you have a vector function of a scalar function, then you will see the chain rule as it applies. And this last one actually does require a bit of explanation. If the magnitude of a vector, or a vector dotted with itself, is a constant, then it will guaranteed be true that the dot product of the vector function with its derivative is going to be equal to 0. Now we also know that it's true that if you take the dot product of two things and you wind up with 0, what we're really saying is that R and R prime are orthogonal. Now 7 is the only one that we're going to bother proving. And it's going to make use of one of the properties that was up here just a moment ago. So we're going to operate under the assumption that R of t dotted with R of t is a constant. What we're going to do is implicitly differentiate both sides with respect to time. With respect to t. Let's not lie to ourselves. T means time. Now over on the right hand side, we're simply differentiating a constant. That's going to wind up giving us 0. On the left hand side, we are differentiating a dot product. And if you'll recall from property number 4, when you're differentiating a dot product, that's simply going to be, well, it looks like the product rule. But since both of these are referred to as R, this is going to wind up being R prime of t dotted with R of t plus R of t dotted with R prime of t. Now the good news here is that the dot product is commutative, which means that these two quantities are the same and therefore can be added together. So 2 times r of t dotted with r prime of t going to wind up being 0. Dividing both sides by 2 gives the desired result. Now we're going to make use of this in a proof in section 3.3, so hold on to your butts for that one.